Hello everybody, my name is John Gardner. I'm a Senior Business Development Manager here at Taylor Hobson, and today I'm going to go through session 2 of a series of webinars looking at Metrology 4, our latest software. For those of you who are new to this software, we're going to go through this coordinate system, but we already have had one session that you can download from our website. That's an introduction to Metrology 4. So if you've not seen that already, you can download from the website. So first thing I'm going to do is take you over to our instrument. Here you can see a virtual instrument. So the way any system that we have that has Metrology 4 will have this virtual instrument. This is a real CAD model of a PGI Novus instrument, a surface finish instrument capable of measuring contour, form and dimension and 3D measurement. This particular system has got a 450mm column. If I just zoom out there, you can see the column. We have a 200mm traverse, and attached to the traverse we have a 20mm gauge. And you'll notice that here we have a stylus with two tips, two diamond tips here. This means that this is a dual bias gauge, so this gauge is capable of measuring surfaces in an upper or lower direction. We also have various other features inside the gauge. It has a lift lower mechanism, a very precise lift lower mechanism that allows us to measure parts with holes or access into bores. We also have on this particular system a Y stage table, so we can use that to manipulate and move the part. An important point is that anything you do with the real instrument will happen with the virtual instrument, and this virtual instrument is an exact replica of the real instrument, and that's what we're going to look at today, the coordinate system and how the virtual relates to the real instrument. So first of all, you have your axes controls down the side. We can move the gauge in and out. We have up and down movement. And as I say, as the real instrument moves, so does the virtual instrument. So you're getting an exact replication of what's happening on the real instrument. And of course, we have the Y movement as well. So if I just press 25mm, you'll see the Y stage move. And if I put it back to, let's put it to 0, you've got 0mm there. I'm just going to, the other thing we have is this lift lower mechanism. If I press park, you'll see the stylus has dropped down. Let me just zoom in that so you can see it again. And I'm just going to set the stylus to a 0 position. In fact, I'm going to move all the axes to where I want them ready for discussion on coordinate measurement system. So I'm going to put X at 100, Z at 200, the Y will be at 0, and the lift lower will be at 0. And here I have an option to move all the axes together. So if I click on there, you'll see everything moves to a set position. So let's discuss the instrument coordinate system, and the way I'm going to do that is I'm just going to move this into a front view. In the front view, I'm just going to zoom out so you can see it. We have the instrument view here. On this view here, we have we have a facility here to fade out the instrument. I'm just going to fade it. I can fade it out completely, so that you can see on this graph here we have a 0 position in X and we have a 0 position in Z. So that's our instrument coordinate systems at 0, 0, 0 position. And what I'm going to just do is add a point on the screen, and you'll see this terminology ICS point. Now ICS just means instrument coordinate system. So I'm going to create a point that's at 0 in X and 0 in Z and press OK, and of course Y. And I'm going to just put a global axis indicator indicator on. So if I just do this, I have now a axis indicator, and I'm in what we call our instrument coordinate system. So what I'm going to do is bring back the instrument. So if I bring that back into focus and then just fade it out slightly and put it into 3D mode, you can see that we have, let's just fade that a little bit more. You can see that we have a 0, 0, 0 position for the instrument coordinate. Now the important point is the 0, 0 position for the instrument never moves. So it's always fixed, okay? And the best way of thinking about moving the instrument is not to think about moving the axes, but think about the stylus tip moving in relation to the coordinate system. Now what I mean by that is if I go to side elevation again, and you can see, just about see the stylus tip there. If I want to move the stylus tip, let's just bring it, let's just move the stylus tip to a positive direction. So if I say move in X, I'm going to move it to 150 millimeters. Look at the arrow here. The arrow is pointing to the right. That arrow pointing to the right is the positive direction for the x-axis, and the arrow pointing upwards is the movement for Z. So movement for Z is in a positive direction going up. So if I hit the x-axis, we're moving off to the right. By the way, if I put a negative value in there, so for example, if I put -50, I can move a relative move, and that's going to move off to the left in the opposite direction to the arrow. If I now go to a side elevation, and this is where I say it's easier to think about the stylus tip moving with respect to the global axis. So here we can see a side elevation. We can see the stylus tip around about where my mouse is. What I'm going to do is go and move the stylus tip to the left, and you can see a left movement should be a positive movement. So if I say let's move the Y stage to 50, I'm actually going to move the stylus tip in a positive direction 50 millimeters. And you can see, although the global coordinate graph is moving, what's actually happening is the stylus tip is moving away from the part coordinate to a 50 mil position. And the reason it's slightly different in Y is because instead of moving what actually in reality happens is the part moves because it's on a Y stage table. But the best way of thinking about this, and what would make life easier, is to think about the stylus tip moving in relation to the 0, 0 position. Okay, so if I want to go and take the Y stage back to 0, click on 0, and you can see we return to the 0 position. Okay, I'm just going to flip back to our side elevation. I'm just going to bring the instrument back into focus so we can see it clearer and clear all the part coordinates. Now, I'm just going to move and check that the instrument right now is at the positions I want. So we have X 100, Z 200, Y 0, and the lift lower at 0. If you look, I can call up the axes by clicking on them down here, and you can see where their positions are. But the important point is the stylus tip. Let me just bring that in. Right now, the stylus tip position, let's just zoom in a little bit. Right now, the stylus tip position within our instrument coordinate system is at X 100, Z 200, and Y 0. And you can see that right now the stylus tip position matches the X, Y, Z positions. However, if I have a lift lower here, and right now the gauge is reading just under 0.2 micron, which is why you see a slight discrepancy in the Z position here. If I go to my lift lower, and move the lift lower to a park position, look what happens to the stylus tip. The stylus tip is no longer at the same position as the axes. It's at 102.9 millimeters in X, and Z it's 190 millimeters. If I just zoom into the stylus tip and call up another option here, which is our cursor positions, you'll see that what's happened in actual fact is the stylus tip has moved to a lower position because we've dropped the lift lower, and it's now moved to the values you see here. The cursor, by the way, if I just hover around the screen, just tells you where you are on the screen. If I go back to set the lift lower to 0, you'll see the stylus tip registers where it is again. And the reason for that is that we know the geometry of this stylus. We know exactly the geometry of the stylus, therefore we know exactly where the stylus tip is in relation to the 0, 0 position of the instrument. What I'm going to do now is just clear these from the screen and show you that this stylus obviously has 2 tips. So how do you decide which tip to show on this stylus tip position? Well, if you have a look at the green arrow just here, you can see currently it's telling us it's in what we call normal bias. Normal bias means that we're working with the lower tip, and it means any measurements we make are on a surface below the stylus tip. However, we have a second tip here, and because this system's capable of reverse bias, we have this option here to change the bias. So if I change the bias, I'm going to put it to reverse bias, but keep just for simplicity, keep the lift lower at 0. Okay, so now you can see the green arrow is now facing upwards, which means we're now working with upper stylus. And look at the stylus tip position now. It's moved from, it's still in the same position in X and Y, but now instead of 200, it's at 238.75. All that means is that that 38.75 millimeter is just a difference between the upper tip and the lower tip. So at any point we know where any of the tips are in space. Okay, right, I'm just going to take that back to normal bias, and we'll take a measurement and show you how the instrument coordinates and the part coordinates match in the analysis. So I'm going to just remove that and go to a measurement. So go to 2DX measurement. We're in normal bias, so I'm just going to call this normal bias. These options here, this means keep results in the instrument view. So when we measure, you'll see the results stay in the instrument view, and we need that for this purpose of this demonstration. Display analysis, that just means that we're going to, when we finish measuring, it's going to show it in the analysis menu. And what I'm going to do is do a measurement at a traverse position of 100 millimeters. So this is the start of the measurement. And then we're going to do a measurement length of 30 millimeters. And we're going to simulate a measurement. And the first thing I'm going to do is append this to a new document. So we're going to create a new document, and you'll see the result shortly. So the first thing I'm going to do is press OK. And what you'll see is a measurement appear on the screen. And this is a simulation of a part. So maybe we can zoom in a little bit more on that result. Now, as we asked for, it's gone straight to Metrology for analysis. What I'm going to do is just show you in studies, go to contour and show you that the coordinate system for this part is the same as the instrument coordinate. So have a look at this first starting point. just here you can see on the left hand side the first data point that we've collected is 100 mil and below 200 mil, around 199.5. So that's the start of the measurement. This coordinate system here exactly matches the instrument coordinate system here. So you can see as we zoom in, it's exactly the same. You've got a measurement at 100 mil and it starts around about 199.5. In fact, you can use the cursor to measure that. So if we hover our cursor over there, you can see the point, the first starting point in the analysis matches that in the instrument coordinate. But of course, right now we're still in instrument coordinates. Now the thing is, this is a reverse bias gauge. What that means is that we can measure upper and lower surfaces. So let's say that this could have been an internal surface. What I'm going to do now is switch the bias over to reverse bias. And remember, what will happen is the stylus tip position will shift to the upper position in the coordinate system. So you can see our green indicator has changed the bias, and we're now at a tip position above the previous position by 37.5 millimeters. What I'm going to do now is just move upwards in a positive direction, just a couple of millimeters in a relative move. Sorry, I'll use the right axes, 2 millimeters, and move up. And then I'm going to move to the 100 millimeter position as we were before with the previous measurement. Okay, so now we're in reverse bias. We're going to take a second measurement. We'll call it reverse bias. Again, we're going to do exactly the same measurements, except this time we're upside down, so we're measuring an upper surface. So we're going to be tracing along the top of the surface here, and I'm going to append to the existing document. So we're going to have two profiles in the same document, one normal bias, one reverse bias. So we'll start the measurement. Okay. On completion, you'll see the result appear in the analysis menu. What I'm going to just do is delete the previous contour measurement and show you the two measurements side by side. If I now select the two measurements together and then go to Studies, Contour, what you'll see is the two measurements appear in the same screen, and because we know the stylus tip position, and this is a very accurate reverse bias gauge, we can correlate the two measurements and do things like analyze diameter and things like that. So, you know, just a quick example, if we could take the radius measurement here, fit a best fit arc to that bit, and I'm going to zoom in on this, fit a best fit arc to this surface. If I just auto scale, what I'm going to do now is just show you I can take a distance measurement from here to here, and there's the diameter between the two centers of each circle. And we could do a lot more, but today we're not going to go through contour. What we want to do is go through the coordinate system. So one of the features we've got here is an option down here to define as datum, define a datum. So what I'm going to do first is one of the features actually on all of our instruments is we have some basic level of contour. We have this ability to define points. So I'm going to show you what we can do. So we're going to define a point at the start and end of this measurement, and one at the end, start and end of this measurement. Once we've done that, what we can do is select this option here define as datum. Click on it and select each point. So we're going to have point here, point A, B, C, and D. Now we can rename these if we want, but we'll keep these as A, B, C, and D. And this is a good example of how to show you that the feedback from the analysis matches the instrument. And we can use this feature to find things like edges and define a coordinate system. So if I go back to the instrument, here's your result. If I go to PCS, you have add datum point from analysis. Click on it, and you see an option here that selects all the PCS points. And again, we can rename this point, but we'll keep them as A, B, C, and D. If I OK this, it will populate all of those points on the screen. I'm only showing you this to show you the feedback process. We're going to show you a video on a real part in a moment and how you would use it. But one of the features I wanted to show is this smart move. So what I'm going to do now is I'm just going to move relative, so downwards. So if I just say -2, you'll see that the column will move down negative in a negative direction. You'll see that we're in reverse bias here. Okay, and I want to move, let's say, to this position here. So what I'm going to do is I'm going to create a 0, 0 point. So in my part coordinate now, instead of instrument coordinate. So watch what happens. Right now I've set this as a 0, 0, 0 point. If I hover over it, it says PCS. PCS means part coordinate system. If I look at my stylus tip position, we're in reverse bias. So I'm just going to move my stylus tip to that position. So let's just right click and say move. And you'll see you have this option of moving X then Z. So I'm going to do that. It'll warn me, by the way, if I'm trying to move an axis too fast. So in this particular instance, I'm just going to press OK, and it's going to move to that position. And now look at the stylus tip position. Currently it says it's at 100 millimeters, Y 0 and Z 241. But of course we've made this now 0, 0 in our part coordinate. So what we can do is there's a facility down the bottom here on the left. You can see currently it says ICS. If I click on it, I'm now working in a part coordinate system. And you can see that the stylus tip now says X0, Y0, Z0. Okay. What I'm going to do is just, and also the same with the cursor position. Cursor position, if I hover around, is currently in instrument coordinates with respect to 0 of the instrument. But if I click on this little icon here, I can switch it over, and now we're in part coordinates. So I can move around within the part coordinate system. So I'm just going to move out of this measurement here. So let's just move 2 millimeters or a millimeter downwards. -1, -2, and then I'm just going to move out this ball here. I'm just going to move now to a 3D mode so you can see the whole coordinate system. So if I go into 3D mode, you can see the part coordinate system. And all I'm going to do is say I'm going to move the Y stage. Let's just move the column upwards, move the traverse back, and move the Y stage to 50 millimeters. And you can see in 3D the whole surface moving. And if I want to move let's change the bias to normal bias, press OK. And now I've flicked to normal bias, but it doesn't matter, I can still move to this position because it knows exactly where I am. and I'm going to move in vectored X, Y, and Z. Press OK, and it'll move our stylus tip to that position. Okay, you may wonder how we can use that. What we can do is we can define edges using this stylus tip, using the coordinate position. So what I'm going to do is run a video of a real measurement on a real part. I think it will be a lot clearer, and you'll see the virtual instrument and the real instrument acting together. So it gives a good indication of how powerful the software is, and what a really useful feature the Smart Move is. So if I'm going to run this video, my colleague Richard Smith is going to go through, and you'll hear his voice on the video now. So there we go.
Hello, I'm going to show you two unique and very useful features in Metrology 4.0 software. These are the Part Coordinate System, or PCS, and Smart Move. So we start by taking a very quick reference trace on the first lead of the ball screw. From this, the origin is defined at 0, 0, and points around the ball screw are also defined, points A, B, C, and D. These are then made available for Smart Move. So you can see the system is now moving directly and rapidly and precisely to the first point, point A, from which the upper measurement is taken. The stylus moves clear. The bias of the gauge is changed automatically. And Smart Move occurs again, taking us to the start of the lower measurement. The lower measurement takes place. The stylus moves off, and the measurements are now completed. In summary, we've seen the part coordinate system, which relates directly to the design drawing, and we've seen Smart Move, which allows us to move very precisely to any point around the part.
Okay, that concludes the webinar. I hope it's been clear enough. Remember, we're talking about instrument coordinate and part coordinate. You will be able to download this webinar from our website, along with session 1, which, as I say, was the introduction. And now I'm going to go over live on the live video so that we can take questions.